Hello, everyone. Welcome back to CPE 517-WS Digital Computer System Architecture course. This is still lecture 1, part 2, Parallelism Taxonomies. I'm your professor, Professor Hang Liu. Okay. So, okay, if you still remember what we discussed in part 1, we said the performance of a single core is heavily reliable on like technology advancement for 50 years until the end of Moore's law, and then we have advanced architecture organization, end of denial scaling, and then Amdahl's law. Basically, go to end of denial scaling and Amdahl's law. This tells us one thing: parallelism is very important. Okay. However, going into parallelism, we face the following challenges. It's a cross-stack challenge. It's not the architecture alone can solve the challenge, okay? Let's say why we have this many challenges. Let's use sorting as an example. So if you guys know sorting, we have bubble sort, quick sort, radius sort, merge sort, etc., right? So if you want to support multi-core sorting, then your algorithm has to be designed in order to support that. For instance, if you do, let's say, bubble sort, like you compare this node with the first node, and this node with the second node, this node with the third node, the number, okay, then you probably have to do this serialized, right? Well, the parallelism comes in, you probably can swap first half and second half, like the merge sort is very easy. So we see algorithm-wise, not every algorithm can be easily parallelized, okay? Okay, if the algorithm can be parallelized, then you have to write it into the program language, the style that is parallelizable. For instance, if you guys remember the pthread or OpenMP or the runnable interface of Java, you have those specific programming descriptive components or derivatives that especially or specifically saying this is a multi-core program. It's different, clearly it's different from the single-threaded program, okay? Once you have those kind of derivatives, for instance, in OpenMP, you have OMP, pragma, those kind of derivatives. You also need a compiler to compile this program, right? For instance, still using OpenMP as an instance. So if you write it in OpenMP, then when you compile it with G++ or GCC, you have to use -f OpenMP, this flag, in order to compile. So that means the GCC and G++ supports compiling the program into a multi-threaded program, right? And then below it, you have to have the operating system that can support multi-core, multi-processor, or multi-threaded execution. And the architecture has to have the protocols like the cache coherence protocol in order to support. And then you have to have the libraries to support that. So we say, if you don't have the algorithm, programming language, compiler, operating system, architecture, libraries, like 6 of them, if any of them was missing, you are not ready to support thread-level parallelism or data-level parallelism for like thousands of cores or chips. And we do want to underscore that architecture alone cannot support 1,000 cores or chips. It is a cross-stack, multi-stack effort, right? Unlike instruction-level parallelism, which we're going to discuss at the first half or first a third of this lecture, like instruction-level parallelism can be exactly achieved by only computer architects, okay? Well, actually, this kind of parallelism, like thread-level parallelism, data-level parallelism, they cannot be achieved without the participation of other stacks. But also, it can also not be solved without the participation of computer architects. So we say it's a is a big precise that requires the efforts from a lot of specs. Okay. Current trends in computer architecture, we see that from 2003, the instruction level parallelism, that is, it's a serial program. Nobody have to do anything with it, and then it can, like, parallel. The users can enjoy the parallelism by themselves without any involvement from programmers or algorithms or compilers. They can directly be achieved by computer architects. Well, that ends. That instruction level parallelism ends in 2003. Okay, the new models for improving the performance are data level parallelism, thread level parallelism, and the request level parallelism. Okay, these parallelisms require explicit restructuring of the application, like what I mentioned in the algorithm, in the programming interface, in the programming language implementation. You have to redo all those programs like sorting, like selection, multiplication, all those kind of algorithms. Like, I have to be honest that I'm in the field of this parallelism, like how to restructure an application in order to take advantage of data level parallelism or thread level parallelism. Okay, you might feel, that sounds to me is very bad, right? So there's a lot of trouble, because in order to leverage this kind of parallelism, we have to redo the entire program stack, like everything. But I'm telling you, be honest, this is why we have so many computer like engineers or programmers, right? That's why we have so many research or job opportunities for you guys. If without that, there's no way people are gonna pay so much money for us to do this. Okay, so we have to say opportunity and challenges are couples. Right? When you have challenges, you automatically have the opportunities to solve those challenges. Okay, so we've been talking a lot about parallelism. Let's see, what is the data level parallelism and task level parallelism, which we mentioned about here. So essentially, if we try to add, we have two vectors, A and B. If we try to add A and B element-wise, like A0 plus B0 equals to C0, A1 plus B1, A2 plus B2, etc. for this, like in total 9 elements. So we say this is data level parallelism. Why? Because the task is the same, right? For every data, like A0, B0, A1, B1, A2, B2, for all of them, the task is addition. Okay, so we see it's data level parallelism for the same task, but we have parallelism across different data. Well, the second one is called thread level parallelism. Oh, sorry, task level parallelism. What does it mean? It means the tasks are different. Well, you parallelize different tasks. For example, A0 and B0, you do addition. A1 and B1, you do subtraction. A2 and B2, you do multiplication and division or and or etc. different operations. So we say you have all these tasks, they are independent, they can be parallelized, but they are different tasks, right? So we say there's data level parallelism and thread level parallelism and data level parallelism and task level parallelism. Sorry, let me recalibrate. So the first one is data level parallelism, and the second one is task level parallelism. Okay. So since we talk about different parallelisms, like the nature of the algorithm, and then when it goes to the architecture or the programming model, we have the Flynn's taxonomies. Okay, that is single instruction, single stream, or single instruction, single data. Okay, or SISD, right? So this is the single-threaded execution, like single instruction, single data can be executed. And then single instruction and multiple data, or SIMD. Okay, I bet a lot of you guys heard about SIMD. It's basically the GPU or vector architecture, or AVX of CPU. It's the very popular simplification of parallelism. Okay, so it's the same as data level parallelism, right? You have a single instruction stream, like single instruction stream here, addition, and then the multi-data stream, sorry, multi-data stream, like you have A0, B0, A1, B1, A2, B2, right? So it's single instruction multiple data is for data level parallelism. And then we have this MIMD, which is multiple instruction for multiple data. So that is a good fit for task level parallelism, right? So we have A0 and B0 with task of addition, or instruction of addition, and A1, B1 with the instruction of subtraction. Okay, so multiple instruction streams and multiple data streams, different instruction goes to different data, something like that, right? So we call it MIMD. And also we have to be honest that there's no MIMD, right? So you have multiple instruction applying to the same data. This kind of parallelism is very rare. I'm not saying it's impossible, but it's not so commonplace. That's why there's no commercial implementations. But for SIMD and SysD, MIMD, for SysD, it's the traditional single core processor. For SIMD, it's the emerging GPU many core or AVX architecture. And then for MIMD, it's the thread level parallelism, or we call it multi-core CPU, right? So those are pretty much the Fning's taxonomies of parallelism. Okay, we're gonna stop here, and then please use 15 minutes to discuss some real-world applications that presents parallelism for SIMD, for MIMD. Okay, looking forward to see that. Okay. Okay, thank you for the discussion. So welcome back to this CPE 517WS Digital and Computer System Architecture lecture series of lecture 1. The part 4 would be a video or 3 videos that discuss the history of CPUs on Canvas. Please use 1 hour to read these 3 videos very carefully, because these are the foundations or very good resources that discusses the computer architecture, and we're going to cover almost all of them. So please go through them very carefully. Okay.